Hello pre-calculus students, and welcome to a video on horizontal reflections and dilations of some parent functions. So we're going to look at a variety of parent functions and just see what happens when we do something on the inside of the function. So the first thing to recognize here is that this number one, we're looking at the function x squared that's going to be horizontally affected, because anything on the inside of the square will be horizontally affected. So let's first just look at x and x squared and just get some key points, and then we're going to see a graph of that, and then we're going to compare it to a graph of what we actually have here. Alright, so we have key points like 0, 0, which is what I sometimes call the anchor point. It's the vertex. We have 1, 1. When we square negative 1, we also get 1. We also have 2, 4, and we can just say we have 4, 16. Okay, we could have said negative 2, 4, but you'll see why in a minute. So let's graph this one, and I'm just going to graph the parent function in red. So we have 0, 0, 1, 1, negative 1, 1. We have 2, 4 right there. And we have 416, which is off the chart, and we already know the basic shape of this, and we already know about symmetry, so there's not really that much point in getting that over here, except to maybe help us to sort of steer the pencil in the right direction when we graph it. All right, now let's look at and see what happens with this function. So now we have x as the input, but the output will be 1/2 x squared. Okay, so if we take the point 0, 0, well, actually, we just take the input 0, we get output still of 0. If we take the input of 1, what do we get for our output? Well, we have 1/2 of 1, and then we square 1/2. So 1/2 squared is 1/4. Okay, we'll graph that in just a minute. If we take negative 1, we put it in, we're going to get the same thing. So we put a negative 1 in here, we get negative 1/2. Square that, and you still get positive 1/4. Okay, so let's look what the graph. Let's go a little bit farther here. Let's get the 2. So if we plug the 2 in, let's see what happens. If we plug the 2 in, we get 1/2 times 2, which is 1. Square the 1, and you get 1. And then last, if we plug the 4 into this one, we get 1/2 of 4, which is 2. 2 squared is 4, so we have the point 4, 4. Let's see what we have now. So we have 0, 0. We have 1, 1, 1/4. It's pretty much impossible to really tell exactly where that is on this particular grid. We have negative 1, 1/4 also. We have 2, 1. So over it, we go over 2 and up 1, so we have a point right there. Okay, and then there's going to be, with symmetry, 1 right there. And then we have 4, 4. So if we go over 1, 2, 3, 4, we go up 1, 2, 3, 4. Now let's see what actually happened here. What actually happened is we can look at this as a horizontal. So let's draw the graph real quick. So let's just kind of draw that. We'll do this. If there's a 4, 4, there's going to also be a negative 4, 4, because we know that this is an even function. All right, now if you look at the graph, you can see that it got wider. It horizontally stretched, and specifically by a factor of 2. Now you can see this by looking at some of the x coordinates. So if you look at this point, for example, it did have an x coordinate of 2, but now it has an x coordinate of 4. This one did have an x coordinate of 1, and now it has an x coordinate of 2. So everything got twice as wide. So when we multiply by 1/2 inside the square, the graph actually does the inverse of that, and instead of getting half as wide, it gets twice as wide. All right, so let's write that down in our observation here. Okay, so in graph 1, the parent function is horizontally stretched by a factor of 2. The parent function, which is y equals f of x squared. I'm just going to pause the video and write it so my hand's not just in your way. Okay, so in graph 1, the parent function is horizontally stretched by a factor of 2. It got twice as wide. When you multiply by 1/2 on the inside, it got twice as wide. Let's look at another graph here. This time the parent function is not the square, but it's the absolute value. And this time we're multiplying it by 3. So instead of a fraction, we're multiplying by 3. So let's think of the parent function first, x, and the absolute value of x. So if you put 0 into here, you get 0 out. If you put 1 in, you get 1 out. If you put 2 in, you get 2 out. If you put negative 1 in, you get 1 out. Okay, and let's just get a little graph of this parent function that we're all familiar with already. So it's going to basically go like this. Actually, I'm going to graph the parent in red. Yeah. So it's going to go through these points right here. It's like the identity function. Then it's going to go through these points on this side. Okay, so something like that. There's the parent. Let's see what happens with this particular function, absolute value of 3x. Okay, so if we plug in 0, so this is going to be x and the absolute value of 3x. And if we plug in 0, we get 0, right? 3 times 0 is 0, absolute value of 0 is 0. Plug in 1, we get a 3. Plug in a 2, we get a 6. Plug in a negative 1, we're going to get negative 3 times, 3 times negative 1 is negative 3. Absolute value of negative 3 is 3. Okay, let's plot these points and see what happens. And we'll add the symmetry because we know this function does have symmetry. So we have 1, 3. 1, 1, 2, 3, right there. We have 2, 6. So 1, 2, 1, 2, 3, 4, 5, 6 right there. And I realize I should have made this one go just a little bit farther so I can see what's happening there. And then we have the symmetry, because this is an even function. So it looks like this time the function got thinner, right? It went in this way. So if we take the point, for example, this point right here, which is 4, 4, on the parent function, sorry, it's 3, 3, it goes to 1, 3. So it actually compressed by a factor of 1/3. This one is, this is 2, 6, so this one is 6, 6, went to 2, 6. Okay, so 6, 6 went in, you can write these numbers down too if you want. 6, 6 went into 2, 6, so you can see what happened is the x-coordinate got compressed by a factor of 1/3. All right, so in this case, in graph 2, the parent function is horizontally compressed by a factor of 1/3. So I'm going to write that down. Okay, so in graph 2, the parent is horizontally compressed by a factor of 1/3. Okay, now let's look at graph 3, and I'm going to pause the video, and I want you guys to graph the parent function, which is the square root of x, and then it's the square root of negative x, what we have here. Okay. Okay, so there's the parent function in red, and those are the points for the parent function. Now, for this function, we can't use the same inputs. I can't input a positive 1 here for x, and then take the opposite of that, because then I have a negative square root. So the only things that I can actually input, in fact, the domain of this function, the domain would be negative x is greater than or equal to 0, which actually multiplied by negative 1, and that's going to turn the direction, that's going to turn the direction of the inequality around. So if you multiply both sides of this by negative 1, you get x is less than or equal to 0. That's the domain for this function with the negative inside. And that's just following the normal rules of finding domain when there's a radical. Okay, so for this function, we can say that in graph 3 here, that the parent function is horizontally reflected. This is horizontally reflected over the y-axis. Okay, so I'm going to write that down. Okay, so in graph 3, parent function is horizontally reflected over the y-axis. Let's take a look at how we can generalize this and just write a couple of rules down. So what we see here in these graphs is that when a is less than 0, that's like case 3. That's when the stuff on the inside, so we have, here's the function that we're looking at. That's the general function, f of x equals ax. That all of these have an a of some kind, 1/2, 3, negative 1. When a is less than 1, a is less than 0, if it's a negative number, then we'd say that the function will be horizontally reflected over the y-axis, just like we said here. We also see that when a is between 0 and 1, so in other words, when it's a fraction, the absolute value is a fraction. So assuming, we've taken care of the reflection, but the number that you have is a fraction, then it's going to be horizontally stretched, and actually it's going to be 1 over a. So if you think about it, this is 1/2, and the stretch here, which was twice as wide, is 1 over 1/2. It got twice as wide. Okay, so we're going to write that one down in a second. And then here, when it's greater than, it's going to be horizontally compressed, like it was here, by a factor of 1 over a. So this was a 3. Here our a is a 3, and the function got compressed from 6 to 2, from 3 to 1. Everything got compressed by a factor of 1/3. So I'm going to write that down. Okay. So we see the general rule here is that when a is negative, f of x is horizontally reflected over the y-axis. Otherwise, we just basically take 1 over a. It's the same thing for both of these. It's always 1 over a. It's just that if a is a fraction, like in this first one, if a is a fraction, then it's going to be stretched, kind of the opposite of what you think when you think of a fraction being in there. And when a is a non-fraction, something where either a is greater than 1 or less than -1, then we just have a compression, horizontally compressed. So it's shrunk like it was in this one. That's the time where we had an a that was not a fraction and it was horizontally shrunk. So we're just going to use these rules now without actually making t-charts to graph a couple of functions. So let's look at the first function, and let's identify what the parent function is, what the transformation will be, and then we'll just graph it from there. We'll still graph the parent function just so we can see that what's supposed to happen is actually happening. All right, so the parent function here, y equals x squared, and the transformation is horizontally, here we can say what the a is also. A is 1/3. That's less than 1, right? It's between, absolute value of 1/3 is less than 1, I mean. And we can say that this is going to be horizontally stretched by a factor of 1 over 1/3. So this would be horizontally stretched by 1 over 1/3 or 3. So it's going to be stretched by a factor of 3. So let's see what that looks like. We graph the parent function, which we're familiar with. We have 2 and then up to 4. So just a quick graph of the parent function. And we're going to get a horizontal stretch by a factor of 3. So these points that I plotted here, if this has an x value of 1, it's going to just be 3, right? 3 times 1 is 3. If this is 2, it's going to go over to 6. 3 times 2 is 6. So 2, 3, 4, 5, 6, so right there. And then with symmetry, it's going to be the same thing on the other side. A -3 here, and a -2, 3, 4, 5, 6 here. And there is our stretched parabola. Okay. Let's try the next one. So we know here that we have the function y equals the square root of x. That's our parent function. And we know that a, in this case, is -1/2. So because it's -1/2, there's going to be a couple of things going on. First of all, that negative is going to be the first row. That's less than 0, so it's going to be horizontally reflected. So horizontal reflection over the y-axis, of course. And then also because a is 1/2, since the absolute value of a is 1/2, so since a is 1/2, it's going to be 1 over 1/2, which is 2. So this one is going to be stretched by a factor of 2. So stretched, and I'll just put times 2. Okay, so I've graphed the parent function, square root of x on the right, and then I took the 1, 1, and I reflected it, and then I stretched it to be twice as far. I took the 4, 2, and I reflected it over to here, I think here, and then I stretched it to be twice as far.